This is Unit 10 on reaction rates and equilibrium. This first video will focus completely on equilibrium. Make sure to create your Unit 10 title page, and on the next slide, create your objective summary page. Here are your objectives and summary page for Unit 10. Make sure to record these in your notebook. Make sure you understand that your objectives for this unit is that you will be able to describe how to express the rate of a chemical reaction and the factors that influence it. You will also be able to describe how the amounts of reactants and products change in a stressed chemical system at equilibrium. And last, you will be able to explain the rate of a reaction and interpret the graphical representation of rates of reactions. Make sure you record this with the word summary so that you can record your summary at the end of the unit. Equilibrium. What is equilibrium? Well, let's first consider this concept. What if we mixed nitrogen gas and hydrogen gas together? Well, at first, the reactants would be put together and the reaction would start. So the hydrogen and nitrogen gas would begin to react. And since there are no products at the beginning, there would be no reverse reaction. There would just be the H2 and the N2 reacting in a forward reaction. But eventually, as the forward reaction proceeds and speeds up, eventually the forward reaction will slow down because the products will build up. And eventually that buildup of products will result in the reverse reaction speeding up, until eventually we reach a point that we call equilibrium, where the reverse reaction is going just as fast as the forward reaction. We call this dynamic equilibrium. What dynamic equilibrium means, or is symbolized as, is a double arrow. So this is an example of dynamic equilibrium. We have our N2O4 going as a reactant, reacting to form our product NO2. And what's happening is eventually the NO2 reacts and forms the reactant again. It goes forward and reverse, from left to right, from right to left, backwards and forwards. This double arrow implies that both reactions are happening and that the process is dynamic. So, what this really means is that the rate of the forward reaction is equal to the rate of the reverse reaction. But what really this means, and what's very important to understand, is that the concentration of the products and reactants overall are actually going to stay the same. But the reaction is constantly running, right? So it's the concentration of the N2O4 and the NO2 from the previous slide remain constant, but what's happening is the forward reaction and the reverse reaction are happening at exactly the same rate, so no net change actually occurs. Keep in mind that one of the ways we can speed up both the forward and the reverse reaction is by adding a catalyst to the system, and that should be a review. We've talked about a catalyst before. So how do we express equilibrium? Well, as always, there's some type of expression for it. So we call this the K expression. K is called the equilibrium constant, and what the equilibrium constant is expressed as is the molarity or concentration of the products raised to their coefficient over the molarity or concentration of the reactants raised to their coefficient. And we'll do a couple of these and you'll get to see what this is like. You're responsible for being able to write a K expression for a reaction that's in equilibrium. You are not required to solve them, just to write them. So, the equilibrium constant, some things to keep in mind. It is products over the reactants, so the right on top of the left. The coefficients are going to become exponents, and then the square brackets, again, just like last unit, mean concentration or molarity. And just to remind you, remember molarity is moles over liters. A couple other things to keep in mind. Pure liquids and pure solids are completely omitted. They're treated as one. Pure liquids and solids have a fixed concentration, which means they will always be constant, so there's really no need to even include them at all. So basically, if you're not including liquids and solids, you're just including things that are gas or aqueous. So equilibrium constants will serve as a measure of the extent that the reaction proceeds towards completion. So if K, the equilibrium constant, is greater than the 1, the mixture contains mostly products. However, if K were less than 1, so if K were less than 1, then the mixture at the end would contain mostly reactants. Okay, so let's do a couple of these and write these. So for example, for this equilibrium system, the K expression would be as you can see down here. So we would not include B because it's solid, so we ignore it completely. For most parts, you can just cross it out. But we do include A. And so A is included inside of brackets to show that that's a molarity of A, or the concentration of A. And then it's raised to the third power because the coefficient for A is the third power. Okay, so 3 becomes your coefficient. So it's products over our reactants. And so on the bottom, we see D is inside of brackets, and it's raised to the first power because there's no coefficient. And we see if we have C raised to the second power because there was a coefficient of 2 in front of it. So this is our K expression for this equilibrium constant. Remember, B was not included because it was a solid. Pure solids and pure liquids not included. They're constant. So let's look at this next one. Now we have a system that's a little bit more familiar. So we have hydrogen gas reacting with nitrogen gas to form NH3. So this is what our K expression would look like. Notice that NH3 is on top, raised to the second power. On the bottom, we have the N2 raised to the first power because there's an implied 1 coefficient there. So there's a 1 implied exponent there. And we see we have H2 raised to the third power. And again, all of these are in brackets. They're all gas, so they're all included. Okay? Let's try this next one. Pause the video for a second and see if you can figure it out. Okay, let's check if you got it right. So notice you would not include nickel because it's solid, or you would not include nickel oxide, nickel 2 oxide, because it's also solid. So really your K expression will just have the CO2 and the CO in it. They're both gas. Notice neither one of these have coefficients, so neither will have an exponent, and it'll be the CO2, the product, over the CO, the reactant. And sure enough, this is our K expression for this equilibrium system. All right, for this next one, take a look. Notice they're all gas, so our oxygen and nitrogen will be on top of our NO. This one will be raised to the second power. And there we go. We see this is our K expression. Let's do another one. So we see that we have 3O2 as a product, and it's gas, so it'll be on top of our O3 raised to the second power as a gas on the bottom. And again, here's our K expression. Okay, so let's try this next one. Notice it's aqueous except for the H2O. So the H2O will not be included because pure solids and pure liquids are not included. So what we'll have is our O2, our hydroxide, OH, on top, raised to the first power. Our NH4 on top, raised to the first power. And then below that, you'll have the NH3 raised to the first power. And so we see this is our K expression. Notice water is not included because water is a liquid. All right, let's try another. So now we have liquid here for water. So that's not included, but it's on top. So we're going to include a 1 to kind of be a placeholder, okay? And then on the bottom, we'll have the O2 and the H2. H2, of course, will be raised to the second power for its coefficient. So we see 1 on top, because the H2O was not included, over the O2 raised to the first power, the H2 raised to the second power from its coefficient. Okay, so that covers our first topic on equilibrium. The next major concept in this unit is Le Chatelier's principle. Okay, and if you need more information on Le Chatelier's principle, there's another PowerPoint to that you can click on here. We're going to kind of walk through that. So what is Le Chatelier's principle? Well, Le Chatelier's principle in the concept is actually pretty easy to understand. It's something that states that if something is changed in a system that is at equilibrium, that system will respond to relieve the stress until a new equilibrium is established. Okay, so I kind of think of it like high schoolers, right? If I add more stress to your life somehow, you're going to do whatever you need to release or relieve that stress. Okay? Now, there are going to be 3 types of stress that will be applied to a chemical system in equilibrium. So we could change the temperature, change the concentration, or change the pressure. All 3 of these are going to be considered a stress to the system. So to summarize that, here's kind of the 6 versions or scenarios you could have happening and what the system will do to kind of release that stress. So if I increase the concentration, the shift will occur away from the increase. If I decrease the concentration, it's going to shift towards the decrease. If I increase the temperature, it's going to shift away from heat. If I decrease the temperature, it's going to shift towards the heat. An increase in pressure away from the gases, decrease in pressure towards the gases, and adding a catalyst is not going to have a shift. And there's a reason for that. If I add a catalyst, it both increases the forward and the reverse reaction, so no net change occurs. I strongly suggest you copy this down into your notes. It's a good quick guide. And we're going to go through each one of these at a time. So we'll go through concentration, then temperature, and then pressure. So first, changing concentration. So if I change concentration, I can add a reactant or product, and that's going to shift the equilibrium away from that increase. Or I can remove a reactant or product, and that shift is going, an equilibrium is going to go towards that decrease, kind of like I'm filling a void. This is like I overloaded one side, so it shifts away from that. This is like I created a void, so it shifts towards that. Okay? So let's start with this first one. So I have this equilibrium system. If the concentration of X right here is increased, it's kind of like I've created an overload on my reactant side. So it's going to shift away from that towards the right. And so this system shifts towards the right in this case. On the next one, I've got the same system, but in this case what I'm going to do is I'm going to take Y and I'm going to decrease it. So I'm going to remove some of Y. Well, now I've kind of created a void right here. So if I decrease this and I remove some of this, it's like A and B have to start reacting to that direction to kind of make up for that and compensate for Y no longer being there. So this will shift towards the left. Okay. This next one, if the concentration of A here is increased, I've created like an overload on the product side. So what's going to happen is this overload over here is going to force it to shift away from that and shift to the left. Okay? Here what I'm going to do is I'm going to decrease B. So I'm going to create a void. I'm going to remove B. And what happens is X and Y start reacting to kind of refill up that B void we created. So it's going to shift towards the right. Alright, so that wraps up changing concentration. Next we're going to do change in temperature. Reactions are either going to release or require heat. We know that already because endothermic reactions were where we had heat was greater than 0. Remember, Q was a positive value for endothermic. So heat will be considered a reactant for an endothermic reaction. Or we have an exothermic reaction. Remember, Q was negative, or delta H would be considered a negative value, and the heat can be considered as a product. That's important to kind of keep in mind. So if we add heat, increase the temperature, it's going to favor away from that increase. If we remove heat, it's going to favor towards the increase. So let's do some of those. So this first one, notice heat's over here as a product. And so if I decrease the temperature, I'm going to decrease the temperature, kind of like I'm removing heat. You can kind of think of this the same exact way you thought of concentration. So if I remove heat, and I decrease it by removing heat, right, it's going to shift towards the right to fill that void. So it's going to shift to the right to kind of fill the fact that heat was removed from the system. All right, here I have heat on the left as a reactant. So if I decrease the heat here, it's like creating a void here. So decreasing heat means it's going to shift towards the left to kind of fill up that void that occurred. And so it's going to shift towards the left. Here it doesn't say it as clearly, but it says delta H is negative. So we've got to think back and think delta H is negative. That's like saying Q is negative. So if Q is negative, that means that Q is on the product side, right? Because this is an exothermic reaction. So if I increase the temperature, then I'm going to increase the heat over here. So I'm creating like an overload on this side. So I'm going to have to shift to the left to compensate for that and make sure that my increase in heat over here kind of gets compensated by this side being overproduced. Okay, let's try this one. Now delta H, which is heat, is positive. So that means my heat is over here on the side with N2 and O2. So if my heat is over here with N2 and O2, it's an endothermic reaction. So if I increase the heat, it's going to add heat to this side and make this side kind of overloaded. So it's going to shift to the right really, really quickly to kind of compensate for that. And when it does that, it's a shift to the right. So it's going to have relieved the pressure and conformed to Le Chatelier's principle. All right, the next stress that we can apply to a system is a change in pressure. So an increase in pressure is going to favor the side that has fewer moles of gas. We're just going to add up the coefficients of the gas on each side. If it's a solid, liquid, or aqueous, we are going to ignore it, okay? A decrease in pressure will favor the direction that has the greatest moles of gas, so the highest number. In a reaction with the same number of moles in the products and the reactants, we're going to say pressure has no impact because there's not going to be an advantage to one side over the other. Okay, so let's consider this one. On this side, I have 1 mole of gas, and on this side, I have 2 moles of gas. So if pressure, when increased, as it's being done in this problem, an increase is going to shift towards the side that has the fewer number. So I have 1 versus 2. So it's going to shift towards the left, towards the 1, because 1 is less than 2. Let's try this one. All right, I've got gas, gas, and gas. So I've got 2 plus 1, so 3 moles over here. And I've got 2 moles over here, so 3 versus 2. I'm going to decrease, and a decrease is going to go towards the greater number. So it's going to go towards the 3, so it's going to go towards the left. Okay? So that's all for this video. We can continue looking at these examples and continue filling in your guided notes. Thank you.